Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss Class 12th Physics Current Electricity, Chapter 3 NCERT Solution, Part 4. Our mission is to provide free classes on YouTube for all students of Class 6 to Class 12, special classes for the students preparing for IIT, JEE, NEET, NDA, and other competitive examinations. Before we begin, we request you to subscribe, like, and share our YouTube channel among your friends and students. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin the chapter. In today's class, we'll start with question number 3.20, part A. Given n resistor, each of resistance R, how will you combine them to get one maximum to minimum effective resistance? What is the ratio of the maximum to minimum resistance? Let us see the solution. So let us start with A. Let us start with 3.20 A. Total number of resistors is equal to n. Total number of resistor is equal to n. Resistance of each resistor is equal to capital R. When n, part 1 of A, when n resistors are connected in series, effective resistance R1 is maximum, given by the product n into R, n multiplied by R. Hence, maximum resistance of the combination R1 is equal to n multiplied by R. Second, when n resistors are connected in parallel, the effective resistance R2 is the minimum, given by the ratio R by n. Hence, minimum resistance of the combination R2 is equal to R by n. So we can write R2 is equal to R by n. The ratio of the maximum and minimum resistance R1 by R2 is equal to NR upon R by n, that is n square. Now let us see 3.20 part B. Given the resistance of 1 ohm, 2 ohm, 3 ohm, how will we combine them to get an equivalent resistance of 1 11 by 3 ohm, 2 11 by 5 ohm, 3 6 ohm, and 4th 6 by 11 ohm? Let us see the solution. The resistance of the given resistor is R1 is equal to 1 ohm, R2 is equal to 2 ohm, R3 is equal to 3 ohm. Equivalent resistance R dash is equal to 11 by 3 ohm. Consider the following combination of resistor. So 1 ohm and 2 ohm are in parallel and 3 ohm are in series. Equivalent resistance of the circuit is given by, that is, R dash is equal to 2 multiplied by 1 upon 2 plus 1 plus 3. Why? Because these two, 1 and 2 resistance, are in parallel and this one is in series. So the value after solving this, we get 2 upon 3 and 3 is plus this 3. So if we solve this one, if we solve this one, the solution will be this 11 upon 3 ohm. Equivalent, second, equivalent resistance R dash is equal to 11 upon 5 ohm. So consider the following combination of resistor. Here this is say 2 ohm, this is 3 ohm, and this is 1 ohm. Equivalent resistance of the given of the circuit is given by R dash is equal to 2 multiplied by 3 and 2 plus 3 plus 1, that is 6 upon 5 plus 1, that is 11 upon 5. Third part, equivalent resistance is R dash is equal to 6 ohm. Consider this series combination of resistor as shown in the circuit. 1 ohm, 2 ohm and 3 ohm are in series. Equivalent resistance of the circuit is given by the sum of individual resistance, that is R dash is equal to R is equal to 1 plus 2 plus 3, that is 6 ohm. Fourth part. So equivalent resistance R dash is equal to 6 upon 11 ohm. Consider the series combination of resistor as shown in the given circuit, that is 1 ohm, 2 ohm and 3 ohm are in series, are in parallel. So equivalent resistance of the circuit is 1 multiplied by 2 multiplied by 3 upon 1 plus 2 plus 2 plus 3, 1 multiplied by 2 plus 2 multiplied by 3 plus 3 multiplied by 1, that is 6 upon 2 plus 6 plus 3, that is 6 upon 11 ohm. Now we'll solve part C. Determine the equivalent resistance of networks shown in figure 3.31. So if we see figure 3.31, A, this resistance combinations is given, and B, this resistance combinations is given. Let us see the solution. CA, part A. It can be observed from the given circuit that in the first small loop, two resistors of resistance 1 ohm each are connected in series. Hence, their equivalent resistance is equal to 1 plus 1, that is 2 ohm. It can also be observed that two resistors of resistance 2 ohm each are connected in series. Hence, their equivalent resistance 2 plus 2, that is 4 ohm. Therefore, the circuit can be redrawn as this. It can be observed that 2 ohm and 4 ohm resistors are connected in parallel in all the 4 loops. Hence, equivalent resistance R of each loop is given by R is equal to 2 into 4 upon 2 plus 4, that is 8 upon 6, that is 4 upon 3 ohm. The circuit is reduced to this now. So 4 upon 3 ohm each resistance. All the 4 resistors are connected in series. Hence equivalent resistance is given in the circuit is 4 upon 3 into 4, that is 16 upon 3. Part B. It can be observed from the given circuit that 5 resistors of resistance R each are connected in series. Therefore, equivalent resistance of the circuit is R plus R plus R plus R plus R, that is 5R. Let us see the next problem. Now we'll see problem number 3.21. Determine the current drawn from a 12-volt supply with internal resistance 0.5 ohm by infinite network shown in figure 3.32. Each resistor has 1 ohm resistance. Let us see the solution. The resistance of each resistor connected in the given circuit is R is equal to 1 ohm. Equivalent resistance of the given circuit R dash is equal to R dash. The network is infinite, hence equivalent resistance is given by the relation R dash is equal to 2 plus R dash plus 1 upon R dash plus 1. So on solving, we got R dash square minus 2 R dash minus 2 is equal to 0. R dash is equal to, we get by quadratic equation, we get 2 plus minus under root 4 plus 8 upon 2. Now output, which is equal to 2 plus minus 12 upon 2, that is 1 plus minus root 3. Negative value of R dash cannot be accepted. Hence, equivalent resistance R dash is equal to 1 plus root 3 is equal to 1 plus 1.73, that is 2.73 ohm. Internal resistance of the circuit is R is equal to 0.5 ohm. Hence, the total resistance of the given circuit is 2.73 plus zero point 0.5, that is 3.23 ohm. Supply voltage V is equal to 12 V, 12 volt. According to Ohm's law, current drawn from the source is given by the ratio 12 upon 3.23, that is 3.72 ampere. Now let us see this problem number 3.22. Figure 3.33 shows a potentiometer with a cell of 2 volt and internal resistance 0.4 ohm, maintaining a potential drop across the resistor wire AB. A standard cell which maintains a constant EMF of 1.02 volt for very moderate currents up to few milliampere gives a balance point at 67.3 centimeter length of the wire. To ensure very low current drawn from the standard cell, a very high resistance of 600 kilo ohm is put in series with it, which is sorted close to the balance point. The standard cell is then replaced by cell of unknown EMF E, and the balance point found similarly turns out to be 82.3 centimeter length of wire. And we can see the figure below. Now few questions has been asked on that. What is the value E? B. What purpose does the high resistance of 600 kilo ohm have? Now let us see the solution. So solution for 3.22 part A, constant EMF of the given standard cell E1 is equal to 1.02 volt. Balance point on the wire L1 is equal to 67.3 centimeter. A cell of unknown EMF E replaced by the standard cell. Therefore, new balance point on the wire L is equal to 82.3 centimeter. The relation connecting EMF and balance point is E1 upon L1 is equal to E upon L. E is L upon L1 into E1. Is equal to 82.3 upon 67.3 multiplied by 1.02, that is 1.247 volt. The value of unknown EMF is 1.27247 volt. Part B. The purpose of using the high resistance of 600 kilo ohm is to reduce the current through the galvanometer when movable contact is far from the balance point. Now let us see the part C. Is the balance point affected by the high resistance? The balance point is not affected by the presence of high resistance. Part D. Is the balance point affected by the internal resistance of the driver cell? The point is not, that is balance point is not affected by the internal resistance of the driver cell. Part E. Would the method work in the above situation if the driver cell of the potentiometer had an EMF of 1 volt instead of 2 volt? The method would not work if the driver cell of the potentiometer had an EMF of 1 volt instead of 2 volt. This is because if the EMF of the driver cell of the potentiometer is less than the EMF of the other cell, then there will be no balance point in the wire. And the last question, that is, do the circuit work well for determining the extremely small EMF, say of the order of a few millivolt, such as the typical EMF of a thermocouple? If not, how will you modify the circuit? F part of the solution is the circuit would not work well for determining an extremely small EMF, as the circuit would be unstable. The balance point would be close to end A. Hence, there would be a large percentage of error. The given circuit can be modified if a series resistance is connected with the wire AB. The potential drop across AB is slightly greater than the EMF measured. The percentage error would be small. Now let us see the next question, that is 3.23. 3.23. Figure 3.34 shows the potentiometer circuit of comparison of two resistors. The balance point with a standard resistance R is equal to 10 ohm is found to be 58.3 centimeter, while that with the unknown resistance X is 68.5 centimeter. Determine the value of X. What might you do if you fail to find the balance point with the given cell of EMF E? So let us see the figure completely. So this is the complete figure. Let us see the solution. Resistance of a standard resistor R is equal to 10 ohm. Balance point for this resistance L1 is equal to 58.3 centimeter. Current in the potentiometer wire is equal to Y. Hence, potential drop across R E1 is, is equal to IR. Resistance of the unknown resistor is equal to X. Balance point Balance point for the resistor L2 is equal to 68.5. Hence, potential drops across X is E2 is equal to Ix. Relation, the relation connecting EMF and balance point is E1 upon E2 is equal to I1 upon I2. Therefore, you can write IR upon Ix is equal to I1 upon I2. X is equal to, we can write L1 upon L2 into R. Putting the value of L1, L2 and R, we get 68.5 upon 58.3 into 10, that is 11.749. So we can write, therefore, the value of the unknown resistance X is equal to 11.75 ohm. If we fail to find the balance point with the given cell of EMF E, then the potential drop across R or X must be reduced by putting a restriction in a series with it. Only if the potential drops across the PM wire, that is potentiometer wire AB, a balance point is obtained. Now let us see the next problem. Now we'll see 3.24. Problem number 3.24. Figure 3.35 shows a 2-volt potentiometer using for the determination of internal resistance of a 1.5 volt cell. The balance point of the cell in the open circuit is 76.3 centimeter when a resistor of 9.5 ohm is used in the external open circuit is 76.3 when a resistor of When a resistor of 9.5 ohm is used in the external circuit of the cell, the balance point shifts to 64.8 centimeter length of the potentiometer wire. Determine the internal resistance of the cell. So let us see the figure, complete figure, and this is the complete figure. Let us see the solution now. Internal resistance of the cell is small r. Balance point of the cell in the open circuit L1 is equal to 76.3 centimeter. The external resistance R is connected to the circuit with R is equal to 9.5 ohm. New balance point of the circuit L2 is equal to 64.8 centimeter. Now the new balance point of the circuit L2 is equal to 64.8. Current flowing through the circuit is equal to I. The relation connecting the resistance and EMF is R is equal to L1 minus L2 upon L2 into R. Putting the value of L1, L2 and R, we get 76.3 minus 64.8 upon 64.8 multiplied by 9.5. So on solving, we get the answer as 1.68. Therefore, the internal resistance of the cell is 1.68 ohm. And this is the end of the solution for chapter 3, electric current electricity. Thank Before we end up, We have a small request. Please subscribe, like, and share our channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you very much for your support and watching our videos.